Hey guys, it's Dr. D-Flo and welcome to my ultimate guide on computer-controlled plasma cutting. Compared to other fabrication techniques, CNC plasma cutting excels in ease of use, affordability, and speed. The perfect trifecta for a hobbyist, small business, or large production facility. This video will start with the workflow of going from an idea to a part, then we'll take a deep dive into the technology in search of the perfect cut. If you're looking for specific information, use the chapters to jump to sections on Toolpaths, torch consumables, Dross, or one of the many other topics covered. This video will end with some fun and useful projects for the plasma cutter. Also, I should emphasize that this guide is applicable to both hobbyist and industrial plasma tables. I will point out which features are only available on high-end systems. And with that, let's get started. To start, I'm going to take you through the major steps of going from an idea to a plasma cut part. First, we must realize our design as a digital model. There are many computer-aided design or CAD software platforms for accomplishing this task, but I prefer Fusion 360 because this program can be used to both create the digital model and generate the code for running the plasma cutter. Here is a model of a vacuum lifter that I'm working on to help move sheet metal around the shop. The frame is composed of steel tubing and plates. For a part to be cut on a plasma table, it must only have 2D features. This flat component that bolts to the suction cups can be plasma cut, but this angled bracket cannot. Of course, a flat version of this bracket could be cut and bent into shape, but for this workflow, we will stick with cutting the flat suction cup plate. With our part identified, we can switch to the manufacturing workspace of Fusion 360. Here we will generate the toolpaths that tell a table where to cut for a dimensionally accurate part. This process is known as computer-aided manufacturing, or CAM. Later in the video, there will be a dedicated section on the intricacies of setting up CAM, but let's keep it simple now. After hitting the Fabrication tab, we will tell Fusion that this part will be created through a 2D cutting operation. Next, we select our tool, which in this case is a plasma torch. The cut settings change depending on the thickness of the material. I store these settings through different torch configurations, which is why even though I only have one physical torch, there are multiple tools here organized by material thickness. This suction cup plate will be cut from 1/4" sheet, so I will select that corresponding tool. Once I click on the part, Fusion will automatically calculate which pass the plasma torch needs to follow to cut out the outside perimeter and interior mounting holes. I can simulate the cutting process to make sure that Fusion got it right. Looks good to me. It's important to note that these coordinate axes in the bottom left corner indicate the reference point or origin of the cutting operation. This origin will need to be assigned to a physical location on the plasma table. That covers the CAM side. I can export the file from my specific plasma table, which is a Shop Sabre Sidekick 8. I'm at my plasma table's dedicated computer with the CAM file loaded up in the plasma software. While manufacturer specific, these interfaces generally look and function the same. Here you can see those same paths generated in Fusion, but they're not currently aligned with where the sheet metal's at on the table. So I need to set that origin point with the plasma torch. I can use the arrow keys to move the torch in the X and Y. I'm aiming for this corner. Once I'm happy with the alignment, I can hit XY0, which of course sets that origin point. X is equal to 0, Y is equal to 0. Lastly, the software also handles the cutting speeds and settings. For some plasma systems, these speeds will need to be set on the CAM side, but on my Shop Sabre table, these are handled in the control. In this drop-down menu, I can select the material thickness and amperage of the plasma cutter. In this case, I'm cutting at 65 amps. The material is a 1/4" mild steel. If I click the config button, you can see all the settings. If I just swap to another material here, you can see that a couple settings here update. We're going to talk about what each one of these settings mean later on, but for now we're going to stick with a 1/4". We'll click done, and this thing is ready to cut. Click start. Now we can watch the sparks fly. And here we have our part. While plasma cutting looks a little bit intimidating with all the sparks, I promise you it's one of the easiest technologies to go from idea to physical part. We need to get into the fundamentals to understand exactly how this works. Let's start at the very top. What is plasma and how is it able to slice through metal? Plasma is the fourth state of matter, distinct from solids, liquids, and gases. But unlike these other states, plasma does not have a distinctive physical structure or surface that you can touch or feel. This makes it a bit more challenging to explain. Plasma is most similar to gas because of its low particle density, but there's a critical difference. Plasma is composed of a mixture of positively charged ions and negatively charged free electrons, while gas is electrically neutral. This ionized state allows plasma to conduct electricity, which for our application, plasma cutting, is the most important feature of this state. An oversimplification would be that plasma can act as an invisible wire. You can see plasma's ability to conduct electricity at work in a neon sign. For this neon tube, there is an electrode at either end. Plasma present within the tube allows the electrons to flow from one electrode to the other. If you've ever touched a neon sign before, then you probably wouldn't believe me that the neon plasma is about 1,000 degrees Celsius. The reason that this tube is not melting through my hand right now is that the plasma in the tube is too diffuse. If we look forward to plasma cutting, clearly we need a lot of plasma to slice through metal. But how do we create plasma? When the neon tube is switched off, not only do the electrons stop flowing, but the plasma returns to its non-ionized gas state. So given this, turning on the power supply must also generate plasma. But how do we rip the electrons away from the gas to form ions? Well, we need a force or a pressure to do this. In an electrical circuit, voltage is equivalent to pressure in a water pipe. If this is sounding foreign to you, definitely look up the water and pipe analogy for electrical circuits, which is great for helping anyone understand the relationship between voltage, current, and power. So we need a set amount of voltage known as the striking voltage to separate the gas molecules from some of their electrons. The striking voltage varies widely based on the gas composition, pressure, and the distance between the electrodes. For this neon tube, it takes about 3,000 volts to initiate the plasma. So yes, neon signs are high voltage and can be a bit dangerous when handled improperly. But once there is conductive plasma, the amount of voltage required to keep the neon tube lit is much lower, typically on the order of hundreds of volts. This is known as the maintenance or operating voltage when discussing neon lights, but in plasma cutting, it is known as the arc voltage. The arc voltage is strongly dependent on the distance between the electrodes. Even this small neon tube has electrodes that are much farther apart than the electrodes in plasma cutting, but more on this in a later section. Let's return to our important problem of generating more plasma and consequently enough heat to melt metal. To do this, we need a high power density. Power is obtained by multiplying the voltage of the circuit by its current draw, and it's measured in watts. This neon light consumes a measly 0.5 watts. The power consumption of an entry-level plasma cutter is on the order of several thousand watts. According to our equation, increasing either the voltage or the amperage can increase the power output of the plasma system. However, there's a practical limit of how high the voltage can be due to safety and cost, so that leaves increasing amperage for more power. In fact, the most defining feature of most plasma cutters are their maximum output amperages. This cutter is called the PowerMax 85 because it has a maximum 85 amps of output. Just having a lot of power is not enough to cut through metal. We have to focus this power to achieve a high power density. With all these things being the same, if I shrunk this neon tube, the intensity of the light per unit length would increase due to the smaller size but same power input. Plasma cutters focus their plasmas through a swirling column of high pressure compressed air, which is one of the several reasons why plasma cutters need not only a high amperage outlet, but also a large air compressor to operate. The gas supply will have its own dedicated section. So I definitely went down a neon lit rabbit hole, but here are the 5 takeaways for this background section. 1. Plasma is a state of matter characterized by its high electrical conductivity. 2. Generating plasma is initiated with a high striking voltage. 3. The plasma is sustained with a much lower arc voltage. 4. High amperage is required to generate an intense plasma to melt the metal. 5. Compressed air focuses the plasma jet. As an aside, I have 2 more glass tubes, one filled with nitrogen and the other one filled with oxygen, the 2 main components of air. The nitrogen glows orange with streaks of blue when turned into a plasma, and the oxygen is white. Most plasma cutters use compressed air, which is the reason why the arc is a bright white, blue, and orange hues. Next, we're going to learn about all the components that are part of a plasma system. When most people think of plasma cutting, they envision the torch with sparks flying out of it, but it's the power supply sitting in the back corner that's doing the heavy lifting. The main purpose of the power supply is to convert AC power from the wall into high amperage DC power. The maximum amperage of the unit will determine its cutting capacity. The general rule of thumb is that a 20 amp cutter can cut 1/8 inch material, and each additional 10 amps will add another 1/8 inch of capacity. For example, 30 amps can cut through 1/4 inch, 40 amps can get through 3/8 of an inch, and so on. Here I have my PowerMax 85 power supply, which is an 85 amp power supply with a cutting capacity of 1 inch. And my Cut 50, which is a 50 amp power supply with a cutting capacity of 1/2 inch. Not only can higher amperage power supplies cut through thicker plate, but they can also cut through thinner material twice as fast compared to a power supply with half the amperage. Unfortunately, it's usually not possible to run power supplies at their maximum amperages for mechanized or CNC cutting due to their duty cycle. Transforming and rectifying the AC power coming from the wall into the correct DC voltage for plasma cutting generates heat within the power supply. The higher the amperage, the more heat that is generated. Beefy electrical components, large heat sinks, and powerful fans are required to dissipate this heat to prevent damage to the circuitry inside of the power supply. If these components are undersized, the power supply must rest every now and then to cool off. The duty cycle lets us know how long the power supply can continuously operate before needing time off. It is defined as the percentage of a 10-minute period that a plasma cutter can operate at its maximum output without overheating. For example, if a plasma cutter has a duty cycle of 60% at 85 amps, it means that it can operate at 85 amps continuously for 6 minutes within a 10-minute period before it needs to cool down for the remaining 4 minutes. When manually plasma cutting, very rarely do you ever exceed the duty cycle because you spend more time positioning yourself, the material, and the torch than you do cutting. However, with a CNC table, the linear actuators are able to quickly move the torch from cut to cut. When cutting many components out of a large sheet, it's very easy to exceed 10 minutes of continuous operation, or very close to that. Most plasma cutters can be run at an amperage that allows for 100% duty cycle. Generally, this amperage is about 15 to 20 amps lower than the maximum advertised. On my website, linked below, I have a roundup of the most popular plasma cutters suitable for a CNC table with their duty cycles and amperages listed. Before purchasing, ask yourself what thickness of material you will be cutting. To cut 1/4 inch plate at 100% duty cycle, you will likely need a 45 amp power supply or greater. If you can afford it, then it's always better to buy a larger plasma cutter to provide the capability to cut thicker materials in the future. Of course, a larger power supply will consume more, power. This can be a problem for hobbyists and garage shops. To appeal to this clientele, there's a category of plasma cutters that can be supplied 110 volts at 15 amps, which is the normal rating on an outlet in a US residence. But the maximum cutting capacity and duty cycles of these units are abysmal. While you may be able to get away with some manual cutting, I would always avoid these 110 volt units for CNC applications. At the very least, a 220 volt receptacle should be used. I have a 50 amp outlet to run my PowerMax 85 at 65 amps for continuous cutting. When running my smaller Cut 50 on my DIY table in my garage, I've been able to get away with a 30 amp 220 volt outlet, which is what most washers and dryers use. Besides the amperage, there are several other features that distinguish a high-end power supply from an entry-level one. First off, on my PowerMax 85, I have this knob here to select different cutting types. The first setting allows for cutting of grate or mesh. Typically, when the plasma cutter goes over the edge of a material, the arc will cut off. This mode maintains the arc as it goes over holes in the expanded metal. The second setting is for cutting plate or sheet, which is the most used. The third is for gouging, where you just want to mark the plate but not cut all the way through it. Gouging requires the torch to be set at an angle and is not commonly used on traditional CNC tables. And the fourth is called trigger lock, which allows you to let go of the trigger when cutting without extinguishing the plasma. You would pull the trigger again to stop the arc. If you don't plan to cut expanded metal or do anything exotic, then these extra settings may not be useful. Entry-level plasma cutters, such as the Cut 50, are always configured for normal plate or sheet metal. This knob controls the amperage, which is common to all power supplies. At the bottom of the front panel, there are connections for the torch and the ground clamp. Similar to our neon light example, where there are 2 electrodes on either end of the tube, the torch represents one electrode and the ground clamp the other. Electrons will flow from the torch to the workpiece, which has a connection to the ground clamp. I've flipped the power supply around, and now we can see the back of it. We've got the power cord, quick connect fitting for the compressed gas with a small water separator, and an electrical connection. This connector is known as a CNC port, and it can be used to send and receive data from the plasma table's controller. The typical communication between the controller and power supply begins with the controller sending a start signal to initiate the plasma arc. The power supply will then send back the state of the plasma arc, known as the arc OK signal. If the arc successfully establishes, then the controller knows that the plasma torch can be moved and cutting will occur. If the arc fails to establish or extinguishes during the cut, then the arc OK signal will become inverted and the controller will pause and send an error to the operator. Most CNC ports, including this one, also provide the controller with access to the arc voltage. As discussed previously, the arc voltage is strongly dependent on the distance between the electrodes, which is the spacing between the torch and the metal sheet. A controller can use the arc voltage to maintain a constant cutting height, even when the stock material is not perfectly flat. This real-time adjustment of the cutting height is known as torch height control, or THC, and will be discussed in its own section. I should mention that the arc voltage, which will be around 100 volts when cutting, would fry your controller if directly exposed to it. An internal voltage divider right behind the CNC port steps this voltage down to one that a microprocessor can safely accept. While this PowerMax 85 does have a voltage divider, some lower cost plasma cutters do not, and an external one is required. It's important to read the manual or test the CNC port with a multimeter to be sure you don't fry all your electronics. CNC ports are not standard on entry-level plasma cutters. My Cut 50 does not have one, but this feature is becoming more popular. So again, check my webpage to be sure you find a power supply with one if you're in the market. Let's turn our attention to the torch and its components, which generate and shape the plasma. There are 2 types of torches. This is a handheld torch for manual cutting, and this is a machine or straight torch for CNC cutting. While the machine torch looks easier to manufacture, this form factor is typically more expensive, and as a result, many DIYers, including myself, have adapted handheld torches for CNC use. The drawback of using a handheld torch on a plasma table is that it's more difficult to mount and manage the leads. It's critical that the torch is perpendicular to the stock material, or else the cuts will be at an angle. For this reason, if it's in your budget, the machine torch is preferred. Here I have a third torch, which differs from the other 2 in the way it ignites the plasma arc. In the neon light example, we discussed that a high voltage, known as the striking voltage, is required to ionize gas and generate plasma. The striking voltage is largely dependent on the distance between the electrodes or the length of the gap that the electricity has to ionize the gas between. To increase the rate of ionization further, the high voltage DC signal can be delivered at a high frequency. This is a bit trickier to explain, but the rapid oscillation of the signal allows for repeated acceleration and collision of free electrons with gas molecules, causing them to lose electrons and form positive ions, which are the ingredients for plasma. So when this third torch is brought close to the metal, it uses a high voltage, high frequency signal to start the plasma stream. This high-frequency start requires no moving parts and is extremely reliable under the right conditions. However, there are 2 issues. The first problem is that this high-frequency noise can interfere with sensitive electronics nearby. This is of particular concern for a CNC plasma table where we have both the motion controller and the PC. Without special grounding and electrical noise filtering, it's not possible to use a high-frequency start plasma cutter in mechanized cutting. I discussed this further in my DIY plasma cutter video. The second issue is that this method cannot establish an arc if the workpiece is covered in an insulating material, such as paint or rust. To cut, electrons must have an electrically conductive path from the torch to the workpiece, back to the power supply, through the ground clamp. It would be a real pain if you had to grind the whole surface of a sheet before cutting it. To solve this second problem, the pilot arc was invented. For the pilot arc, the workpiece is not the anode or second electrode needed to complete the circuit. Instead, the anode is inside of the torch. When you pull the trigger on a torch equipped with a pilot arc, the electrons jump from the cathode, which is always inside of the torch, to the anode, which is now the nozzle. Compressed gas passing through this narrow arc becomes ionized, turning into plasma. That pilot arc can melt insulating materials such as paint on the workpiece and clean away rust. So why do you still need a ground clamp for this plasma cutter if it has a pilot arc? Because both electrodes and resulting arc are confined within the torch, these components experience a lot of heat and wear. For this reason, most plasma cutters have the pilot arc operating at a lower current to protect the torch. Therefore, the pilot arc is not strong enough to melt all the way through a metal sheet. But it is strong enough to clear the way for the main current arc to establish with the now cleaned metal. Once the main or transfer arc has ignited, the pilot arc circuit is turned off. As a side note, if you see plasma, but your torch is failing to cut through the material when the table is run at the correct speeds, then it's likely that your pilot arc is failing to transfer to the main arc. The cause of this problem is almost always an issue with the ground connection. I hope the role of the pilot arc is clear. It is absolutely necessary for CNC plasma cutting because a pilot arc results in consistent main arc ignition, no matter the surface condition of the workpiece. But the pilot arc doesn't solve the electrical noise problem created by the high frequency start. To solve this problem without purchasing expensive electronics, another innovation is required: the moving or blowback start. Any amount of space between the electrodes, even the small distance present within the torch for pilot arc ignition, requires a high frequency spark. But what if there was no space between the electrodes? Well, this is the idea behind blowback start. If the cathode and anode are touching, then the electrons have no problem traveling through the torch and back to the power supply. In fact, this configuration results in a short circuit. Now imagine that the cathode starts to retract or move backwards while the current is flowing. This movement is made possible by a spring-loaded mechanism. As the cathode moves, it creates a small gap between the electrodes. At first, this gap is imperceivably small, allowing the current to ionize the small amount of gas there without high voltage. As the cathode continues to move backwards, the gap between the electrodes gradually increases. However, even with this growth, only a few more molecules of gas need to be ionized to bridge the previously ionized material and reach the anode. This gradual growth of the gap allows for the formation of a larger and larger plasma arc without the need for a high-frequency spark. The cathode and spring assembly is actuated through carefully timing the flow of compressed air, which will try and escape through the nozzle, but can't until it has moved the electrode back from it. This is a clever idea that Hypertherm invented in the 1980s. The patent has since expired, so many entry-level plasma cutters now feature blowback start and are compatible with CNC tables. If you've ever wondered how to determine if a plasma cutter that you have access to has blowback start, then you can remove the shield and the nozzle and press on the electrode. If the electrode is spring-loaded, then it's a good chance that this torch features moving or blowback start. I do want to point out that all blowback start plasma cutters have a pilot arc, but the other way around is not true. High-frequency plasma cutters can, and most do, have pilot arcs for cutting through insulated materials. Again, that list on my website will be helpful for selecting a suitable plasma cutter with blowback start. This torch right here for my FineCut 50 is one of the very few that is high-frequency start without a pilot arc. Next, let's disassemble the machine torch and discuss the internal components, which are often called consumables because they wear down with use. First, we have the shield. As its name suggests, the shield protects all the other components from sparks and molten metal. For continuous cutting, such as with CNC tables, a shield is a must. Most handheld torches cannot be fitted with a shield, and as such, the upstream components will wear out quicker as they're hit with the molten material. Here you can see that the nozzle is directly exposed. Just for comparison, there the nozzle is on the straight torch, hand torch, and of course, the shield covers the nozzle up. This is just another drawback to adapting a manual torch for computer-controlled cutting. The shield needs to be replaced when there's a buildup of material on the inside wall. Next is the nozzle, which focuses the plasma energy, resulting in a precise and controlled cutting action. The plasma jet exits the hole in the middle of the nozzle, restricting it to a particular diameter. The size of the orifice is determined by the amperage setting on the power supply. Here I have a 45 amp, 65 amp, and 85 amp nozzles. The 85 amp nozzle has the largest orifice. With a larger exit diameter, you get more airflow through the torch. This has several important implications. The first is that you have increased cooling of the consumables, which is critical at higher power. The second is that a higher amperage arc will ionize gas quicker, and to keep the plasma from extinguishing, you need to feed the arc at a higher rate. And third, the gas plays an important role of ejecting the molten material after the plasma has melted it. If you're cutting thicker material or cutting faster, then more molten metal needs to be removed per unit time, hence higher airflow is needed. But there are several drawbacks associated with using a larger orifice, the first being worse cut quality. Plasma is not like a straight knife, but instead it is a complex, oval-shaped spinning ball of very hot gases. A larger orifice will increase the diameter of the plasma that makes contact with the material. The larger the plasma is, the more likely an artifact such as rough or angled surfaces will be left on the cutting edge. We will discuss the shape of the plasma and how it is formed when we get to the Swirl Ring consumable. Another issue with a larger plasma jet is that the material missing after the cut, known as the kerf, is greater. A large kerf will prevent the cutting of fine detail. To demonstrate the proportional relationship between kerf width and nozzle size, I performed 4 test cuts on an 11-gauge sheet, each with a different nozzle orifice. The power supply amperage and table settings were adjusted for each setup. The first cut used a nozzle with the smallest orifice and is known as a FineCut nozzle. I've not mentioned this type of nozzle yet, as it will have its own section, but what is important is that this nozzle has the smallest exit diameter of the 4 tested. After the FineCut, the next 3 cuts are from the 45 amp nozzle, then the 65 amp, and finally the 85 amp. During this demo, you can see how speed scales with amperage. The 85 amp was able to sever the material almost twice as fast as the 45 amp one. At a quick glance, you can probably already tell that the FineCut and 45 amp nozzles had the smallest kerf widths. But a quick caliper measurement shows that the FineCut has a kerf of 1.26 millimeters, the 45 amp with 1.41 millimeters, the 65 amp with 1.6 millimeters, and the 85 amp with 1.79 millimeters. The approximate half a millimeter or 20,000ths of an inch difference between the FineCut and the 85 amp nozzles may seem insignificant, but when cutting out ornate designs, you will want the smaller kerf to prevent tiny details from being destroyed by the plasma stream. Further, regardless of what nozzle and amperage combination you cut with, it's important that the kerf is taken into consideration when programming the cut, or else the features will be undersized. Compensating for the kerf is discussed in the later cam section. So, for the best cut quality and achieving the finest details, you want to use the smallest nozzle and amperage rating that will cut through the material. But this will come at the cost of speed. Quality and production rate are inversely related in plasma cutting and, frankly, most manufacturing techniques. You never want to use a nozzle at any amperage but the one it's rated for. Using too high of an amperage will cause premature wear on the nozzle and upstream components. But if the amperage is too low, then the arc will become unstable as it's being fed too much gas. If you're experiencing poor cut quality out of the box, make sure the nozzle matches the amperage. Finally, during the cutting process, the nozzle is surrounded by the intense heat of the plasma. This thermal stress leads to a gradual erosion of the orifice, leading to a larger diameter. And as discussed, this will change the dynamics of the plasma, leading to poor cut quality and a larger than expected kerf. It's difficult to provide an estimate of how long a nozzle will last before needing to be replaced. Unless there's a failure where part of the nozzle blows out, leaving an irregularly shaped orifice, then the cut quality will slowly degrade over time. If you're cutting fine details or looking for a tight fit-up, the nozzle may need to be replaced more often. For the work I do on my table, I usually swap nozzles after a day of cutting, which amounts to several hours of arc on time with hundreds of ignitions. Premature nozzle wear indicates that there's an issue with the cut settings, amperage of the power supply, or quality of compressed air being supplied to the torch. After the nozzle, we have the cathode, which is usually referred to as just the electrode. The electrode is responsible for emitting electrons, which will ultimately bombard the nearby gas, forming the plasma. Most of this component is made from copper, but while conductive, copper is not the best element at emitting electrons. To improve the efficiency at which plasma is created, a hafnium or zirconium insert is placed at the center of the electrode, which you can see here. The inclusion of these transition metals leads to better arc starting and improved stability. During the cutting process, the electrode is surrounded by the intense heat of the plasma. This thermal stress leads to a gradual erosion of the electrode. As the electrode wears, the distance between the electrode tip and the workpiece may increase, requiring higher energy levels to maintain the same cutting performance. Also, this erosion causes the electrode to pit, resulting in irregularities of the plasma and, of course, the cut. Similar to the nozzle, any amount of wear will affect the quality of the cut, but I wait until the pit reaches about 1 millimeter or 40,000ths of an inch greater than the starting depth before replacing it. If you wait too long to replace the electrode, it will start to sputter material, destroying all other components in the torch. If the plasma arc glows green, then you have burned up the hafnium insert, leaving only copper. At this point, the electrode is close to catastrophic failure and should have been replaced a while ago. The life of the electrode is less dependent on the cutting time, but more on how frequently the torch is ignited. Every time an arc is produced, the electrode experiences a huge negative surge, pulling away atoms from its surface. Plasma cutting designs with many separate elements will require more starts and stops of the plasma arc, which of course will cause the electrode to need to be replaced sooner than will be the case for long continuous cuts. I work on a little bit of everything from detailed signs to thick structural steel, and I see several days of cutting life out of an electrode. Premature electrode wear can be caused by contaminants in the compressed air supply, especially water, poor cooling of the torch, or excessive use of the pilot arc, which is common when cutting mesh or starting the torch too far away from the material. Hypertherm has integrated the spring and electrode together, which makes it very clear that this is indeed a blowback start torch. Some manufacturers have the spring farther up in the torch, such as the case for the Cut 50 and most other entry-level plasma cutters. Upstream from the electrode, we have the swirl ring, which channels the compressed gas. For the most precise cuts possible, the plasma needs to be shaped into a narrow column with enough momentum to remove the molten metal from the cutting region. The swirl ring functions as a mini tornado generator. Let's walk through how it forms a vortex of air. Inside of the torch, compressed air is on the outside of the swirl ring, and to pass through the orifice of the nozzle, the air must go through these holes that travel the circumference of the swirl ring. If you look closely, the holes are angled in a specific direction to impart a rotational motion to the gas as it passes through. When installed correctly, this swirl ring will cause a clockwise rotation of the air when the torch is viewed from the top. This directionality of the swirling plasma results in one side of the cut having a more square or straight edge, which is preferred. Of course, one edge of the cut will belong to the desired part and the other to the scrap material. It's critical that the squarest edge is on the part, which can be controlled by the direction which the torch travels to cut out the part. For torches with clockwise swirl rings, which nearly all of them have, as the torch moves away from us, the squarest edge will be on the right. Therefore, for external features, the torch needs to be cut in the clockwise direction. To demonstrate this, I've cut two squares, one where the torch took a clockwise path and the other where it went counterclockwise. The difference in edge quality is quite apparent where the counterclockwise square has the most bevel. If I wanted my final part to be a square with a hole in the middle, then cutting this internal feature clockwise will cause the squarest edge to be on the scrap material because that edge was on the right side of the cut. If I measure the two sides of the circle near the surface, you can see one side is smaller than the other, indicating a bevel. Switching the torch's motion to counterclockwise for internal features is a must to keep the internals part edge to the right of the plasma. Here we see less bevel, but there's still a slight difference in dimensions between the two sides of the hole. In a future section, I will also talk about why you cannot achieve a perfectly square edge on either side of the cut due to the oval shape of the plasma. Generally, depending on the material's thickness, a 2 to 4 degree bevel is about the straightest edge you can achieve. For those new to plasma cutting, this may be a bit confusing, but fortunately when programming the plasma cutter, there is usually a radio button or a drop-down menu that allows you to select how to compensate for this swirling motion of the plasma and keep the squarest edge on the part and not the scrap. We will discuss this further in the cam section. What is important to take away from this section is that the direction the torch travels to cut out the part matters for edge quality, and of course is dependent on the directionality of the swirl ring. In regard to having to replace the swirl ring, while this is a consumable component that can crack after use or have debris lodged in its holes, this does not happen frequently. But it is important to inspect the swirl ring every time other consumables are replaced or when experiencing poor cut quality. The last consumable is the retaining cap, which as its name suggests, retains all the previously mentioned components. Unless the torch is crashed or not being cooled properly, the retaining cap is unlikely to need to be replaced. In addition to holding all the components together, this retaining cap has a spade connector for a feature known as ohmic sensing, which allows the torch to find the top of the material prior to cutting. A future section on touching off the material will go into more detail on this technology. When you go to reassemble your torch, you may find that your plasma cutter fails to fire or throws a warning. The likely cause of this is that the parts in place switch has not been triggered. You can see here on the bottom of the torch that this button will be pressed if all the components are seated properly, and the retaining cap has been tightened enough. This is a safety mechanism that almost all torches have to make sure everything is installed properly. I went to quite a bit of effort explaining all the different consumable components, but if other companies follow in the footsteps of Hypertherm, then the previous discussion could become purely academic. What I'm alluding to is Hypertherm's new SmartSYNC cartridges, which combine the shield, nozzle, electrode, swirl ring, and retaining cap as one replaceable cartridge. Even though all these components wear at different rates, the benefits of this system is that when you replace the cartridge, everything should just work. The cartridges use RFID chips to communicate to the new sync power supplies, which will then change the cut settings and set the appropriate amperage depending on whether you are cutting or gouging and which nozzle size is being used. The sync cartridges also track their life and suggest when they need to be replaced. To be honest, when the new SmartSYNC cartridges were announced, my first thought was that Hypertherm was tired of aftermarket consumables undercutting their prices by a factor of 4 with similar quality. For example, these 85 amp nozzles look identical, but one is a genuine Hypertherm nozzle that costs $7.30 without shipping, and the other is a clone from Amazon with a price tag of $1.90. To purchase an 85 amp SmartSYNC cartridge, you will have to cough up $53. From the outside, this looks like a cash grab, especially since Hypertherm can keep out aftermarket cartridges with the RFID chips. But I became less pessimistic over time, especially with how the price of steel has refused to decrease. If the cartridge can keep the consumables from failing during a cut or prevent you from selecting the wrong amperage, then they are likely to pay for themselves. Also, if you're constantly swapping between different nozzle sizes, then the end-of-life tracking makes it so you don't have to inspect the components before swapping to previously used cartridges. Right now, my table is not equipped with a sync torch or power supply, but I wanted to mention it to keep this video relevant in the future. The last Hypertherm-specific invention that I want to quickly mention are their FineCut Consumables. These consumables include a special shield, nozzle, and swirl ring, which are specifically designed for plasma cutting applications that require precise and high-quality cuts, especially on thin materials. The nozzle has a finer bore, which allows for a narrower, more controlled arc, resulting in reduced kerf width and improved cut quality. There is more innovation in the FineCut line than besides the small bore, but for simplicity, I'm going to keep it to that point. When I'm cutting out designs with a lot of details, especially those that include lettering, I always use FineCut Consumables with the power supply set between 40 and 45 amps, depending on the thickness of the material. The drawback, of course, of a finer bore is that only thin materials can be cut. The maximum thickness for FineCut Consumables is 10 gauge or approximately 4 millimeter thick steel. The last important ingredient for plasma cutting is the compressed gas. In the previous sections, I talked about the 4 important roles of compressed gas in the plasma cutting process, those being 1, a source for generating plasma, 2, a vortex for focusing the plasma, 3, a force for ejecting molten material, and 4, a mechanism for cooling the torch. Clearly, if we don't supply the plasma cutter with enough gas, then it won't be able to operate properly, if at all. As discussed previously, higher amperage power supplies will consume larger quantities of gas, but even entry-level units can quickly gobble up more air than a small tire compressor can generate. The gas flow rate and pressure for a 40 amp cutter starts around 4.0 cubic feet per minute at 70 psi, which is equivalent to 113 liters per minute at 4.8 bar. My PowerMax 85 uses 6.7 CFM at 85 psi, or 190 LPM at 5.9 bar. Compare these values to the 2.6 CFM at 90 psi capacity of this pancake air compressor commonly seen at hardware stores, and it should be clear that we need something larger. However, you don't want to go out and purchase an air compressor that matches the requirements of your plasma cutter exactly, or else it'll be constantly running, which causes 2 problems. The first is that air compressors have their own duty cycle, with most being around 50 to 75%. They need time to rest or else they will burn out. The second issue is that the temperature of the air inside of the tank increases with the frequency at which the compressor runs. As the air temperature rises, its ability to hold moisture also increases. I liken this to having a muggy day in the summer, but never in the winter. Water moisture and plasma cutting are incompatible, and we will discuss drying the air later in this section, but it's best not to exacerbate this problem by purchasing an undersized air compressor. Ideally, you want a compressor with at least 50% higher output than the consumption of the plasma cutter. The air compressor that I'm using is this Craftsman 80-gallon 2-stage 175 psi unit. It's rated for 13.5 CFM at 90 psi, which is almost exactly twice what I need for the PowerMax 85. While this unit is great at supplying air, it has the drawback of using oil as a lubricant and sealer between the pistons and cylinders. A small amount of this oil can make it into the storage tank, and just like the water moisture, it must be removed before making its way to the plasma cutter. But before we get to drying and filtering the compressed air, I want to quickly cover the other plasma gases that can be used for cutting. While compressed air is by far the most economical plasma gas source, it results in a poor to average edge quality on most metals. When cutting mild steel, the nitrogen in the compressed air can diffuse into the heated metal, forming incredibly hard nitrides. This process is known as nitriding and is not desirable because the plasma cut edge will be difficult to machine and weld due to its hardness. Further, the nitrides are brittle, which can lead to cracking or fracturing of the edge under mechanical stress. The ideal gas for cutting mild steel would be pure oxygen, but only very specialized cutting systems can handle this gas because internal components need to be selected as to not degrade or even explode in the presence of pure oxygen. So for mild steel, we're stuck with compressed air for nearly all but the most industrial plasma cutters. Fortunately, the edge on these mild steel parts are still relatively clean, albeit difficult to work with after cutting. But when cutting aluminum, compressed air leaves a visibly poor edge. However, this time it is the fault of the oxygen content in the air. The molten aluminum will react with oxygen or oxidize, leaving a rough, porous edge. Instead, nitrogen is recommended for the plasma gas. My PowerMax 85 is compatible with nitrogen, but always confirm with your manufacturer to be sure that a particular gas can be used. Here you can see me hooking up the nitrogen bottle to the plasma cutter. No filtering or drying is needed because the gas is high purity. Unfortunately, I can only handle small gas cylinders in my shop, and this size will only last for about 15 minutes of cutting. This example does help emphasize the point that compressed air is a much more economical plasma gas. But take a look at the plasma cutter slicing through aluminum with a nitrogen plasma gas. Here you can see the improved edge quality of the part cut with the nitrogen compared to the compressed air. Before we move on, I do want to mention that you should not cut aluminum over an ordinary water table, as I've done. The dangers of this will be discussed later, but I drained and cleaned my water table after cutting those quick test pieces. The last material I will quickly mention that can benefit from a specialized plasma gas is stainless steel. I save this one until the end because you may think that given the nitriding in the mild steel that you would want an oxygen plasma gas. But stainless steel contains chromium, which readily oxidizes similar to aluminum. For this reason, a predominantly nitrogen gas is preferred. Hypertherm actually recommends a 95% nitrogen and a 5% hydrogen mixture known as F5 for cutting stainless steel. The addition of the hydrogen increases the temperature of the plasma, allowing for a quicker cut with a cleaner edge. I, however, do not cut stainless because the plasma arc can vaporize and ionize the chromium present in the material. This can lead to the generation of hexavalent chromium, a highly toxic compound known to cause lung cancer. A respirator and proper ventilation are needed for cutting stainless steel. But here are some images of the edge quality when cutting with compressed air versus F5 for stainless. 99% of the material that I'm cutting on this table is mild steel, and plasma cutting is the most economical way to cut this material when using compressed air as the plasma gas. But as I alluded to, we need to clean up the air leaving the air compressor. Large particles will clog the narrow paths the air takes through the torch. Aerosolized lubricants can degrade the plastic tubing and fitting inside of the power supply. And water moisture, the worst of all, negatively affects the plasma cutting process in nearly any way imaginable. Just a couple examples include causing the plasma arc to misfire, cooling the arc leading to poor edge quality, and faster degradation of the electrode and nozzle. I would go so far to say the #1 problem for beginners is that they are not using dry enough air. I'm next to my air filtering setup, and this is the minimum that I would recommend and would be undersized if you plan on running your plasma table daily. I'm fortunate that my shop is air conditioned, which goes a long way to keeping the moisture from getting into the compressed air. Remember, the hotter the air, the more moisture it can hold. But let me walk you through my setup. This is a 4-stage filtering and drying unit from HTP, where the air comes in from the left and is first filtered to remove any particles larger than 40 microns. This is slightly smaller than the width of a human hair. Next, the air flows into this coalescing filter, which has a high surface area medium inside, allowing aerosols and very small particles to come together and form larger droplets, which can be removed from the air. The second stage filters down to 0.03 microns, which is smaller than a virus. The third stage consists of a 2-quart or 1.9 liter desiccant bed, which further removes humidity from the air. The desiccant beads only have so much capacity to absorb water before they need to be recharged. When they turn a translucent pink, they need to be thrown into an oven to bake out the moisture before reuse. Blue is when they're dry. But how much water does the third stage remove? The dryness of air is quantified by its vapor dew point, and that is the temperature at which the moisture in the air will condense into water droplets on a surface. When the air is cooled to its dew point temperature, it becomes saturated, and any further cooling will cause moisture to condense. As a result, the lower the dew point temperature, the less moisture there is in the air. This desiccant removes humidity from the air to a temperature of -3 degrees Fahrenheit or -19 degrees Celsius. But my PowerMax 85 requests a water vapor dew point less than -40 degrees Fahrenheit, which is the same in Celsius. This is very dry air, and to achieve this level of dryness, a special refrigerated dryer is needed. This instrument is currently out of my budget, but for the best cut quality and longest consumable life, then it is necessary. But back to what I have. The fourth stage is just another filter to remove any desiccant dust that was picked up by the air in stage 3. Finally, we have the pressure regulator. The inlet pressure will depend on your specific plasma cutter, but usually the pressure rating is the minimum operating value. For my PowerMax 85, it accepts 85 to 135 psi. When you're using a torch with long leads, which are common for CNC tables, you'll want to supply a pressure on the higher end to compensate for the pressure drop that will occur along the length of the torch. I'm using 110 psi, but again, your specific value will depend on your system. All the air is piped with these 3/8 inch ID hoses with quick disconnects. They sell hoses with the same disconnects, but they have a 1/4 inch ID. These can restrict the airflow. I have recommended hoses, air dryers, and other compressed air related products on my website, so check that out if you need help selecting the right pneumatic components. The last connection to be made is to the air dryer on the back of the plasma cutter. It's kind of misleading that these plasma cutters include this woefully undersized dryer, as it can mislead users into thinking they have dry air. Perhaps it's to prevent a catastrophic amount of water entering into the system if someone were to connect their compressor directly. But this is not sufficient for all the reasons that we just discussed. That was a long conversation about plasma gas, but it's such an important variable that dictates the success of your cuts. Let's switch back over to talking about the shape of plasma. As mentioned in the Swirl Ring section, the plasma is funneled and focused with a vortex of gas. Ideally, this plasma would be shaped into a cylinder, as this would generate a straight cut regardless of where the plasma contacts the workpiece. However, several complex phenomena cause the plasma to be preferentially drawn towards the anode or the workpiece, creating an elongated or oval-shaped plasma. Consequently, it becomes very important where the plasma intersects with the workpiece. If the torch is too high, the cut will occur at the bottom of the plasma, creating a positive cut angle. If the torch is too close to the material, the workpiece will catch the top of the plasma, creating a negative cut angle. Looking at the edge of a cut part can give you insight into whether the height of the torch is set correctly. Here you can see an edge with a positive angle due to too high of a torch, and here is the opposite, with the torch being too close to the material. The goal is to hit the workpiece with the middle of the plasma, as this region has the least curvature. Unfortunately, it's not possible to completely eliminate angularity, but you can get close, especially with thinner materials. Now that it's clear why the cutting height is so important for edge quality, we can jump into our next two sections on touching off and torch height control, which are features that establish and maintain the correct cutting height respectively. Touching off, or initial height sensing, is the process of the torch finding the top of the material. If the height of the material is known, then the torch's Z position can be set such that the plasma cuts the material with a region of low angularity. As discussed previously, this would be the center of the plasma stream. Touching off is largely a feature of the CNC table and not the plasma cutter. Entry-level plasma tables may require the starting height to be set manually by loosening and then tightening a sliding mechanism. While low cost, this manual adjustment is prone to errors and severely limits the size of the sheet metal that can be cut. The reason that this manual adjustment would limit the cutting capacity is because sheet metal, especially higher gauge or thinner material, is not necessarily flat. Exacerbating the problem is that the slats, which support the stock material, build up with slag as you use the table. So likely bowed sheet metal is sitting on bumpy, uneven supports. Not good. All this to say that a starting height that may be appropriate in the bottom left corner may be too close or too far away for the other end of a 4x8 foot sheet. Technically, you could manually adjust the starting height before each cut, but this is tedious and eliminates the greatest advantage of plasma cutting, its speed. There are two ways that plasma table designers automate the initial height sensing. The first method involves placing the torch on what is known as a floating head. This mechanism allows the torch to move upwards when it contacts the material beneath it. When the floating head assembly moves up far enough, it will trigger a switch, signaling to the controller that the torch has found the top of the stock material. My DIY plasma table uses a floating head, which has worked great, but I have noticed two drawbacks. The first is that the floating head is the slower of the two methods because the torch has to touch the material and then continue down far enough to trigger the switch at the top of the floating head. This extra Z movement adds a noticeable amount of time at the start of each cut, but this is only a small issue. The second and larger problem is that the stock material must oppose the downward movement of the torch to force the floating head upwards. This physical interaction can deform thin sheet metal, resulting in too low of a starting height. The severity of this problem will depend on the thickness of the material and the spacing of the slats. Anything thinner than 24 gauge or 0.5 millimeters is likely too flimsy for a floating head. However, there is one considerable benefit to this technique, and that's its tolerance to different surfaces. The floating head can pick up the height of a painted, wet, or rusty material. The second touch-off method is known as ohmic sensing, which is what my Sidekick table uses. The term ohmic refers to electrical resistance, and as such, this method uses the electrical resistance between the plasma torch shield and the workpiece to determine torch height. As the torch is brought closer to the workpiece, the electrical resistance will decrease. If the shield and metal are allowed to touch, the resistance will be almost zero. The controller uses this resistance to appropriately set the torch height. With this sensing method, the torch only lightly kisses the material, allowing it to touch off even the thinnest sheet metal without deforming it. Also, after probing, the torch can immediately move to the cutting height, allowing for quicker starts. There are also fewer moving parts with ohmic sensing. The only addition is this wire, which provides an electrical connection to the shield through this metal component on the retaining cap. Of course, reading the resistance is more complex than waiting for a switch, as is the case with the floating head, so usually a more plasma-specific controller is needed for a table that uses ohmic sensing. The glaring drawback of ohmic sensing is that the resistance will change depending on the surface of the workpiece. Rust and paint will increase the resistance, leading to erroneous starting heights. After the table has established the correct torch height by touching off, how does it keep this ideal separation between the material and the torch constant during the cut? As mentioned, the sheet metal is not sitting flat on the table, so for long cuts, the height will have to be adjusted while the torch is moving. This process is known as torch height control and is the topic of our next section. In the power supply section, I showed you the CNC port that provides several different signals to the plasma table's controller. One of those signals is the arc voltage. When cutting, the electrical arc will stretch from the electrode in the torch to the metal sheet or plate. The voltage required to maintain this arc will be dependent on its length. Let's say that the torch is cutting a piece of metal that is bowed upwards. If the torch stays at a constant height, then the metal will get closer to the nozzle as it moves along. In this scenario, the arc length is decreasing and so is the voltage. At first, the cut will have a negative angle as it catches the top of the plasma stream, but eventually, if not corrected, the torch will crash into the workpiece. Fortunately, the controller board does not have to sit idly by. It can respond to the decreasing voltage by raising the height to increase the length of the arc and voltage back to its previous value. This feedback loop is known as torch height control, or THC. The arc voltage sets the distance between the torch and the material during the cut. There is not one ideal arc voltage value, but instead each metal and material thickness will have a slightly different value. A cutting chart in your plasma cutter's manual will provide a starting arc voltage for you to optimize around. If you don't have such a table, or the reported values are yielding poor cuts, then you can change the target arc voltage by investigating the edge of a part. If you see a positive cut angle and the voltage is too high, and a lower arc voltage should be set to drop the torch. If you see a negative cut angle, the arc voltage needs to be increased. It should be noted that arc voltage increases as the consumables wear, so the voltage setting will need to be increased to maintain proper torch to work distance over the life of consumables. Seasoned operators will be able to adjust the arc voltage in real time based on its appearance. Unfortunately, most entry-level plasma tables do not have torch height control as a standard feature, but I think it is absolutely critical when cutting sheet metal larger than 2 by 2 feet. To recap achieving and maintaining the proper cutting height, first, a floating head or ohmic sensor brings the torch close enough to the material to allow for the pilot arc transfer to the main arc. Once established, the plasma arc voltage provides feedback to the controller, which maintains a constant cutting height regardless of how flat the workpiece is. Next, let's zoom in on the plasma cutting sequence. Let's say that we want to cut out a square from this 1/4 inch material to analyze the cutting process. The first step is for the plasma cutter to come down and touch off the material to find its height. Before the torch can be moved along the program path, the material must be pierced so that the molten metal can be ejected out of the backside. If the torch is moved before piercing the metal, then not only will you have an incomplete cut, but molten metal will be flung along the top of the material, which is known as splatter. When first piercing, this top splatter cannot be avoided as there is nowhere for the newly melted material to go but up. The torch needs to be far enough away such that the splatter does not find its way up into the nozzle, damaging the consumables. The distance between the torch and the material during a pierce is known as the pierce height. This height is between 2 to 3 times the cutting height, with thicker materials having a greater pierce height to avoid the proportionally larger splatter. Once at the correct spacing, the torch fires and dwells in this spot. The pierce delay is how long the plasma cutter waits until beginning the cut. Again, the pierce delay must be long enough that the arc can pierce the metal and will be dependent on the thickness of the metal. Once the pilot hole has formed, the material will be ejected out of the back of the workpiece, so it's now safe for the torch to move down to the cutting height. During the pierce and adjustment of the torch height down to the cutting height, the arc voltage can be erratic. For this reason, the torch height control is not turned on until after this process has completed and the arc voltage has stabilized. The length of time the THC stays inactive at the beginning of the cut is known as the torch height control delay. Thicker materials will require a longer delay. Now we can watch as the torch tracks along the square profile, with the THC making small adjustments in the torch spacing along the way. At the end of the cut, the torch extinguishes the plasma and backs away. There will be a short period where the compressed air is still flowing through the torch to cool the consumables. While our square looks good, how do we know that we cut it at the right speed? Could we have gone faster to save time, or would decreasing the speed result in a better edge? This question will be tackled in the next section. Perhaps the most important setting in CNC plasma cutting is the cutting speed. If set too high, then the plasma will not have enough time to cut all the way through the part. If set too low, the plasma will have too much time and it will be able to expand its search for material outside of the usual curve. While it would seem to be easier for an operator to tell when the cutting speed is too high, as it would not be possible to punch the part out of the stock material, there are a range of fast speeds where the plasma will cut through the material, but the edge quality will be quite poor. When you deviate from the optimal speed, the consequence will be more work on the back end as you will have to clean up the dross before proceeding to later assembly steps. Let's define what dross is, as its absence is a key indicator on when we have hit the speed sweet spot. Dross refers to the rough and irregular buildup of partially melted metal on the cut edge of the workpiece. It indicates that the material has not been cut efficiently. Dross can form from both cutting too quickly and too slowly, with each condition having a different appearance. Let's start our analysis with high-speed dross, which forms as a thin, linear bead of solid metal on the back side of the cut. This dross is difficult to remove and must be grinded off. When you increase the cutting speed to increase the productivity of your table, you typically end up with high-speed dross, which requires more post-processing time to clean up. This, of course, is counterproductive. High-speed dross forms when the arc significantly lags behind the torch. Here you can see two scenarios of the arc underneath the material that is being cut. The top view has an arc that is in line with the torch, while the bottom view is angled behind the torch. With the arc lagging behind, it does not have enough time to melt and eject the material, resulting in dross. This arc angle is an important variable in plasma cutting. Near the perimeter of sheet metal, you can usually catch a glimpse of the arc under the material, which can help you adjust the speed during a cut. But make sure you are wearing properly shaded glasses as the arc is very bright. Next, let's look at the opposite scenario of cutting too slow. Low-speed dross forms as a bubbly deposit at the bottom of the cut. This type of dross can be easily chipped off, and usually large segments go flying when hit with a flap disc. While easier to remove, low-speed dross can indicate that your kerf will be larger than expected, causing parts to be undersized. The reason you're left with a larger void when cutting slower is because the plasma arc will search and melt material outside of its path if allowed. When the plasma melts material on its edge, there is less airflow to eject the molten material, which tends to drip rather than be blown away. The drops of molten metal can fall back onto the cut edge, resulting in low-speed dross. Let's take a look at the arc angle that occurs during too slow of a cut. Here the arc is angling ahead of the torch as it searches for material. This indicates that the cut needs to be faster. I should mention that a vertical arc does not result in the best cut quality. In general, a slightly lagging or inclined arc angle is preferred. Here is an example of an ideal arc angle for this 1/4 inch material. However, due to it being easier to remove low-speed dross, it is better to err on the side of a vertical arc than one that lags too far behind. Viewing the arc angle during a cut can be difficult as most of the time it's obscured by the material. However, after the cut, you can see the position of the arc based on lag lines that are left behind on the edge of the part. To demonstrate this, I cut out a series of 1/4 inch thick squares, starting at a cut speed of 1500 millimeters per minute, with each subsequent square being cut at 500 millimeters per minute, faster than the previous. The 7th and 8th squares were cut at too high of a speed to be severed from the material. Here you can see the lag lines on the edges of the squares. For the slow cutting speeds present on the early squares, the lag lines have a slight C shape to them. This results from the bottom of the arc moving ahead of the torch. For the later squares with faster cutting speeds, the lag lines are S-shaped, where the bottom of the S is parallel to the bottom edge. This view also helps illustrate how that high-speed dross is formed. We want the lag lines near the bottom of the cut to not be curved forward or backwards, but straight up and down. For this example, square 4, or 3000 millimeters per minute, has the ideal lag lines and incidentally the least amount of dross on the back side. It's also worth noting that if dross is on the top edge, then the cut height or arc voltage is too high. Before optimizing speed, you must have the correct torch to work distance as previously discussed. I hope it's clear how examining the dross and lag lines can help determine whether to increase or decrease the cut speed. Most plasma cutters are supplied with tables in their manual that can get you close to that dross-free window, but as the consumables wear or as you search for faster production rates, you'll have to put your detective hat on and read the edge of the cut. In the next section, we'll discuss the design of CNC tables. Of course, the table has to be able to move fast enough to prevent low-speed dross. You may have noticed in the previous section that the square cut at the ideal speed had dross on its corners. This occurs because my table has to deaccelerate to change directions. The longer it takes for the gantry to change speeds, the more likely the table will pass through regimes where the speed is too slow, producing dross. This is a limitation of all tables, but some are worse offenders than others. There are quite a few plasma tables available, covering both the hobbyist and industrial markets. This isn't going to be a buyer's guide per se, but I do want to zoom in on 3 specifications that you should consider when purchasing a table. Those specs being speed, material capacity, and fume control. The table speed is critical for cutting accurate parts with minimal dross. For a set material thickness, you can cut with a higher amperage to get faster production rates. But the table must be able to move the torch reliably at these speeds. For example, a 3mm or 11 gauge steel sheet should be cut at 3800 millimeters per minute with 45 amps, or 6800 millimeters per minute with 85 amps. Thin materials such as 0.5mm or 26 gauge sheet can require speeds north of 12,500 millimeters per minute or 500 inches per minute, even at 45 amps. It's important to identify your material and production rates before selecting a table. I opened up this section by emphasizing the importance of acceleration. There's no point in having a table that can travel at high speeds if it can't accelerate to this speed within its work envelope. Plasma cutting likes smooth motion, and a jerky acceleration that causes the table to shake will translate to a rough cut. However, a quick but smooth acceleration will require a sturdy gantry and frame, which will weigh more, and of course, this will affect your acceleration. It's easy to get caught up in acceleration and speed values, so I wanted to distill this conversation down to 2 features that you should opt for if production rate is a priority. The first is to find a table with servo motors. Across the board, these motors have higher accelerations and speeds than stepper motors. The second feature to opt for is either a ball screw or rack and pinion transmission, which converts the rotation of the motor to quick linear moves. Low-cost machines, such as my DIY table, typically use lead screws, which are slower than a ball screw or rack and pinion. The next specification that you should consider when looking for a table is the material capacity. I mean this both from a size and a weight perspective. Sheet metal, especially steel, is heavy. A 1/4 inch thick 4x8 foot sheet can weigh over 300 pounds. Double this thickness to 1/2 an inch and you have a sheet that weighs almost 650 pounds. Thick plates are often too heavy for aluminum extrusion tables to support, and a steel frame is needed. But the deciding factor for me to upgrade from my DIY table to this industrial shop saver table was not its speed nor weight capacity, but instead its ability to cut standard 4x8 foot sheets. My local steel distributor sells sheets in 2 sizes, 4x8 and 5x10. To get material that could fit on my DIY table, I had to either purchase the full sheet and manually plasma cut it down to 2 by 2 foot squares, or have the supplier cut it, which added extra cost and delayed pickup. Also, a larger cutting area means larger parts. It wouldn't have been possible to plasma cut my mill enclosure with a smaller DIY table. If you have the space and budget, I highly recommend a table that can handle at least a 4 by 8 foot sheet or metric equivalent. Anything smaller will require you to jump through hoops to get material on your table. The final design criteria that I'm going to cover is fume management. The plasma cutting process generates fine particles, toxic metal vapors, and harmful gases. While all three of these byproducts are important to consider, the fine particles that are created when the plasma melts and blows away the metal are the most problematic, as it can quickly coat every surface in your shop. Tables that do not collect these metallic particles are known as blow-through tables and should be avoided. The most popular fume management solution is a water table. When cutting, the molten material is ejected into the water, which traps the small particles and fumes. When the water level is set to about a 1/4 inch beneath the material, nearly all particles will be captured along with most of the harmful smoke. The smoke you do see is steam caused by the bottom of the arc vaporizing some of the water. Personally, I have my water level below what is recommended for fume control, because if the water is too close to the material, it can splash up and cool the molten metal before it's fully ejected, causing slightly more slag. I also have plenty of ventilation in my shop, and my garage door is open when cutting. In addition to having slightly more slag on the bottom of cuts, the other drawback of a water table is rust formation. As you are familiar with, uncoated steel will develop a reddish-brown texture through the chemical reaction of iron with oxygen and moisture. This rust can affect the conductivity of the workpiece and the slats that support the sheet metal, which will degrade the cut quality. Fortunately, this rust can be prevented by introducing a rust inhibitor, such as sodium nitrite, into the water table. I use a concentrate from Sterling Cool that prevents both rust and organic growth. The other fume management solution is the downdraft table, which uses powerful fans to suck debris and smoke down into the table and out of the shop after passing through a filter. This design is a more premium option that not only costs more upfront, but also to operate, as you have to pay for the extra power and filters. But it is a cleaner solution, as you don't have dirty water splashing out of a water pan. However, it is my opinion that the downdraft table is only a good value proposition for those who plan to cut a lot of aluminum. In a later section, we will discuss the precautions that need to be taken when cutting aluminum on a water table, but to conclude this section on table design, the best table for you will depend on what you plan to cut. Check with your material supplier to determine what the standard sizes for sheet and plate are, and definitely make sure your table is equipped with fume management. In the last section, we talked about the size and weight capacity of the table, but what is your shop's capacity to move and store sheet metal? Again, I started with a smaller DIY table, and I initially had my steel supplier cut all my sheet metal down to 2 by 2 foot squares. While a bit heavier for a thicker plate, I was able to pick up the steel and place it on my cutter without trouble. I knew that larger 4 by 8 sheets would be heavier, but it didn't really dawn on me that a single person can't load this size sheet onto a plasma table. Thin material is too floppy to handle without grabbing both ends, and thicker material is too heavy. I'm still struggling with this problem and have had to rely on manpower to load sheets onto my table, but I'm running out of favors, which is why I built the vacuum lifter. But before we talk about that, I want to quickly mention that I first tried to use magnets to load sheet metal. Ignore my sketchy setup. Magnets work well for picking up thick plate. I was able to move anything thicker than 6 millimeters or 1/4 inch with these two 880 pounds or 400 kilogram lifting magnets. The reason that magnets can't be used for anything thinner is that if the sheets flex or deform, then the magnets will quickly lose their grip. Also, the holding force for each magnet is dependent on how thick the material is. This graphic on the side of one of the magnets shows you % holding force as a function of material thickness. There's almost no holding force for anything under 5 millimeter thickness. The other issue I had with the magnets is that you can't pick up a single sheet from a stack. Instead, the magnetic field will penetrate several sheets, and it's difficult to separate them when this occurs. So for these two reasons, I decided to build a vacuum lifter, which uses 8 large suction cups to stick to the top of sheet metal at evenly spaced points. The size, number, and rubber-like material of the suction cups enable them to quickly and easily grab a hold of thin material and stay adhered even when the sheet flexes. Each cup is rated for 125 pounds, allowing, in theory, 3/4 inch 4 by 8 foot plates to be picked up. But in practice, I will be able to safely move 1/4 inch material and thinner, even if a few suction cups lose their grip. This is not expected to happen, but a 3x safety factor is always welcome. Next, I'll walk you through the electronics and pneumatics of the vacuum lifter. 8 separate 12-volt vacuum pumps apply 15 inches of mercury of negative pressure to their corresponding suction cup. A solenoid controls whether the cups are exposed to vacuum or vented to release their hold on the material. Individual vacuum gauges are used to confirm that each cup has sealed to the material. The cups are spring-loaded to help them conform to a sheet that may be sitting on an uneven surface. These buttons on the control panel determine which cups are active. Being able to control the suction cups individually will be useful if I need to pull a large part off the table, but not the entire sheet. I decided to go with electric motors instead of a Venturi vacuum system so that the lifter could be completely wireless or tubeless. It's powered by a 20-volt DeWalt battery. There will be a montage of me building this vacuum lifter at the end of the video, so stay tuned for that. To move the vacuum lifter around, I'm using my engine hoist, but the eventual goal is to use these slots here with a forklift. A couple million views on this video would go a long way into helping me afford that piece of machinery. So if you haven't already, hit the like button and leave a comment about your favorite section or tip on this video. For the most enthusiastic viewers, consider hitting that join button to provide a monetary contribution to my educational content. And with that, we will move to our next section on cutting aluminum. When most people think plasma cutting, mild steel is probably the first material that comes to mind. However, plasma cutting is one of the most affordable ways to cut aluminum. If you're jumping around this video, make sure you check out the plasma gas section where I compared cutting aluminum with compressed air versus nitrogen. The quick synopsis is that a pure nitrogen plasma gas provides a better cut with less oxide formation, but the edge quality from the compressed air is pretty respectable. Usually the presence of oxides would cause porosity when welding the plasma cut edges. However, with my pulse MIG setup, I couldn't see the difference in weld quality between parts cut with compressed air or nitrogen plasma gas. All the settings for cutting this material are readily available in most manuals. I made this section to discuss the dangers of cutting aluminum over a water table, which has the potential of creating an explosion. During cutting, small particles of aluminum and aluminum oxide form. These particles sink to the bottom of your water table where the aluminum oxide absorbs the oxygen in the water, leaving hydrogen gas behind. Most of this hydrogen will rise to the surface as little bubbles before popping and diffusing into the air. However, some of this gas will not make it to the surface, but instead will be trapped by slag or forgotten about parts that fell to the bottom of the table. Over time, a relatively large bubble of hydrogen could form, and because hydrogen is a highly flammable gas, this buildup will explode when the hot plasma arc passes over it. The hydrogen gas is also produced slowly over several days after your last cut. If you leave a large piece of sheet metal on the table, then the hydrogen can collect underneath it, which is particularly dangerous. If you cut aluminum without draining the table, then it's always recommended to remove any sheet metal for overnight storage. If you plan to cut a mixture of steel and aluminum, then a water table is still the best option from a cost and fume management perspective. So to prevent the buildup of this explosive gas, the bottom of the water table must be agitated to free trapped bubbles. This is most often accomplished with a bubbler. Low-cost solutions use fish tank aerators, but industrial tables have pipes that run along the length of the table with small holes allowing compressed air to escape and displace the hydrogen gas. To conclude this section, while aluminum can easily be cut, you have to be careful with the hydrogen byproduct. Next, we're going to get into the digital side of plasma cutting by discussing how to efficiently pack parts and generate toolpaths through computer-aided manufacturing, or CAM. Before I switch over to the computer, make sure you stay tuned for the end of the video, which showcases some of my favorite plasma projects. By design, computer-controlled machines mindlessly follow the code that you generate on your computer. This code, which is often referred to as Toolpaths, is created through computer-aided manufacturing, or CAM. For plasma cutting, an error at this step can be quite costly because to maximize efficiency, you typically cut out multiple parts in one go. Failing to correctly compensate for the kerf, setting the incorrect cutting speed, or making a number of other mistakes can lead to poor quality parts or incomplete cuts. It's difficult, if not impossible, to fix mistakes after the fact. Usually you have to eat the cost of the sheet metal and try again. So for this reason, 90% of the work that goes into CNC plasma cutting takes place at the computer as you make sure that the toolpaths correctly represent the final physical part. In this section, we will look at how to turn both 3D models and DXF files or sketches into toolpaths. A couple disclaimers. One, I will not be showing you how to create digital models or sketches, just how to cut them out. And two, I will be demonstrating this workflow in Fusion 360. You may have access to a different CAM or Plasma-specific software. However, the features that we will be discussing are common across all these different programs, but may fall under a different name. Let's say you want to plasma cut a fire pit. Fortunately, most of the popular plasma cutting designs are available online for a small fee. I found this octagon fire pit and grill on Etsy. In the file name, you can see that this design can be manufactured several different ways, including plasma cutting. Also, DXF indicates that the file is supplied in at least this format. Briefly, DXF files are like vector or SVG files, but they are dimensionally accurate. While you can plasma cut dimensionless vector files, you have to scale them to the right size. You cannot cut raster image files like JPEGs and PNGs. These have to be run through a special conversion software, which typically only works if the image is black and white. That process is out of the scope of this video. I purchased, downloaded, and inserted the DXF file for the fire pit in Fusion. These blue lines indicate that this is only 2D data, which is sufficient for driving the plasma cutter. This first step is a Fusion-specific one, as other softwares will automate this, but I will draw a rectangle that represents the stock material that this fire pit will be cut out from. In this case, it will be a 4 by 8 foot sheet. I will then use the Move tool to position all the pieces within the sheet metal. This process is known as nesting. Later, I will show you how to nest automatically to speed this up and minimize how much sheet metal is needed. Next, we will switch to the manufacturing workspace of Fusion and then click on the fabrication tab. The first step is to establish an origin for all future toolpaths. Toolpaths are really just mini coordinate pairs that the plasma torch follows, and of course, coordinate pairs are X and Y distances from the origin. To establish our coordinate plane, we will click the Setup button. The yellow shading represents the work area or stock material size. Because we drew the rectangle for standard sheet metal, the work area is almost correct. However, I don't like where the origin is because it's more difficult to find the center of a sheet than, say, the left corner. I can switch the position of the origin with the stock point option. Now the origin is in my preferred location. On my plasma table, the y-axis is twice as long as the x, and consequently, I need the longer 8-foot length of the stock material to be paired with the y-axis. I purposely imported the DXF file and sketched that rectangle such that the design would be in line with the setup of my table. But if you need to swap which axis is which, then you can use this drop-down menu. If I switch over to the stock tab, Fusion likes to add a 1mm buffer to the sides of the stock material. With my workflow, I always turn this offset off because it adds material that's not actually there. Our setup is complete now, so we can click OK. Next, we'll generate the toolpaths by clicking on the Cutting or 2D Profile button. A dialog pops up that contains all the settings needed to make a cut. First, let's select our tool. There are two factors that affect our cut settings: the plasma cutter's amperage and the thickness of the sheet metal. Higher amperage or thinner material requires a faster cutting speed, but kerf is also affected by those parameters. A higher amperage and a thicker material will result in a wider kerf. While I only have one plasma torch, I use this tool library to automatically set the kerf width and speed when I select a tool that matches my material thickness and amperage. I will be cutting the fire pit out of 3mm steel with 45 amp FineCut Consumables, as there are some narrow slots. If I edit this tool, navigating to the Cutter tab, we can see that the kerf will be 1.3mm when using this setup. In the Cutting Data tab, I also have the appropriate cutting speeds, cut height, pierce height, and other relevant plasma settings that we've discussed previously. Interestingly, the motion controller for my Shop Saver table will ignore all these settings, and I will have to set them when I get to the plasma table's computer. This is just a quirk of this specific machine. My DIY table, on the other hand, uses the speeds and other cutting parameters from Fusion. The reason I still fill out all these settings for my Shop Saver table is that when I simulate a cut, I will have an accurate estimate on how long it will take. Your table or motion controller will come with documentation on what settings need to be bundled with the toolpaths when they are exported from the CAM software. However, it is critical that the kerf width is set appropriately in the tool settings, as most modern plasma controllers do not compensate for the kerf, and it is your CAM's responsibility to offset the toolpaths to ensure that the part does not come out undersized. We will dive into this more in a second, but I'm going to close these settings and select the tool. Immediately, the feed rate or speed of the cut updates. Navigating to the Geometry tab, here is where we select the sketch profiles that will be turned into toolpaths. I'm just going to click on one of the side pieces for now. It immediately highlights and a red arrow appears. If I click OK and zoom in on the dark blue toolpath that was just generated, you will notice that it is on the inside of our part. Further, the entry and exit points, which are indicated by these red and green dots respectively, are also on the inside of our part. So not only will we get an undersized part, but our edge will be messed up by the torch leading in and out of the cut. Not good. The reason that this occurs is that Fusion has a hard time telling what is the part and what is scrap material when just working with 2D sketches or DXF files. Fortunately, we can tell Fusion that it has it backwards by going up to the browser and editing the one cutting operation under our setup. Then we go back to the Geometry tab. Our profile is highlighted again, but this time we want to click the red arrow to make it switch directions. This can also be accomplished by checking reverse in the dialog associated with the chain or profile. Click OK again. Now we can see that the toolpath is correctly on the outside of our part. The reason that it is not directly on top of the profile is that Fusion is automatically compensating for the kerf that we set in our plasma tool. Let's take a look at kerf compensation by editing our cutting profile, but this time we will go to the Passes tab. Fusion compensates both for the kerf and direction of the torch in one setting called sideways compensation. Recall that the direction the torch cuts the part out, either clockwise or counterclockwise, will determine the cut quality. We want clockwise for outside features and counterclockwise for inside features. Fusion calls this type of compensation left because as the torch is making a cut, the motion that it travels keeps it to the left of the part. That way, you've got the best edge on your part. Simulating the cut shows the torch moving clockwise around the exterior of the part. Fortunately, for 99% of all cutting operations on 99% of all tables, you will never change this setting. But just to demonstrate, if you click center, there is no kerf compensation as the toolpath is right on top of the original design. And if you select right, then it cuts counterclockwise as shown in this simulation, but still compensating for the kerf. It's strange that Fusion combines kerf compensation and direction of the torch in one setting, but it's fortunate that you rarely ever change it from the default left. As mentioned previously, most modern motion controllers require the path to come pre-compensated or offset to accommodate the kerf. For those controllers, it is important that the compensation type is set to in computer, as in do it now on this computer. Briefly, the last setting I want to talk about in the Passes tab is how corners are handled. The table has to deaccelerate when approaching corners in order to change directions, which results in low-speed dross. You can decrease the amount of dross by allowing the table to round the corner, which means that it doesn't have to come to a complete stop before changing directions. Or the other option is to form a loop around the corner. This takes longer but gives us the best of both worlds, a sharp corner and minimal dross. Take a look at how the loop looks in the simulation. Finally, in the linking tab, we have the last important group of settings, which deal with the lead in and lead out. We don't want to ignite the torch directly on top of the toolpath because the initial pierce splatters molten metal on the top surface. The rule of thumb is that the lead in and out distances should be at least the thickness of your metal. Even for thinner material, I tend to not drop this any lower than 5 millimeters unless I'm cutting small internal features such as a hole. To demonstrate the problem with lead-ins on small internal features, let's say I want to cut this slot out on the bottom plate of the fire pit. With my previous settings, I get a warning and no toolpaths. The warning even says that there is a problem with one of the settings in the linking tab. If I use the measuring tool, we can see that this slot is only 3.5 millimeters wide, so clearly we can't have a 5 millimeter lead-in. If I use a lead-in value of 1.5 millimeters, it is able to generate the toolpath. I just need to spend a little more time cleaning up that edge, but this is a limitation of the design. It is quite common, especially for slot and tab designs. So I will often create different cutting operations for small features that need a short lead-in and larger features that do not. Now I could go through and click on all the different profiles and contours in this DXF design, but Fusion just works better when everything is a solid with some sort of depth. If I head back to the design workspace and extrude everything 3 millimeters to match the stock material thickness, I can then go back to the manufacturing workspace and edit the cut settings again. With the parts being solid, I can click on each part once, and Fusion automatically knows which direction to offset the toolpath. I still take a close look at all the toolpaths and simulate them before exporting, but once I am satisfied, I can right-click on the cutting operations and click Create NC Program. From here, it is important to use a post-processor, or POST for short, that speaks the language of your table. Nearly all commercial machines, and even most controllers for DIY CNC machines, have a POST somewhere in Fusion's library. After hitting export, we have the file that will run on the plasma table. When plasma cutting a single part or an assembly with only a couple components, it's easy to position those sketches or solid bodies close together to conserve material. But when it comes to more complicated designs, such as my mill enclosure, configuring the sheet can become a time-consuming puzzle. Also, if you make a change to the original model, you may have to repack the parts, which adds more work to the design phase. To aid in the layout of parts, most CAM packages include an automatic nesting solution that organizes parts as tightly as possible. Unfortunately, with Fusion, there is a monthly fee to use this nesting feature, but with the high prices of steel and the value of your time, it's easy to justify this cost if you're using your table for production. Fusion has videos and written guides for how to use this feature to its full potential, but I'm going to quickly run through the workflow just to demonstrate how convenient it is. For this example, I will use my mill enclosure model, which is currently one of my side hustles as I sell weldable kits on my website. I have the 3D model configured to be resizable for different benchtop mills, so I frequently tweak the dimensions and re-nest the parts. To start the nesting process, we navigate to the Utility tab in the Design workspace and click Nest. This dialog contains a list of all the parts that Fusion will attempt to organize on the sheet metal. But some of these components are not meant to be plasma cut, such as the casters, drawer slides, acrylic windows, and several other parts. We can select Ignore on these items. Clicking through some of the components, you can see that the parts need to be cut from either 6.35 millimeters, which is 1/4 inch thick material, or 1.5 millimeters, which is 16 gauge material. Of course, Fusion will make sure that the components of different thicknesses are not placed on the same sheet. Once satisfied with the parts that are selected for nesting, we click OK and head to the manufacturing workspace where we want to be on the Fabrication tab. Clicking on Component Sources, we see the parts that were selected in the previous dialog, but with additional information such as material type. In this case, all the parts will be cut from steel. But similar to the different material thicknesses, if you had a second material, say aluminum, then those parts would be placed separately from the steel ones. There are some other controls, such as aligning the parts according to grain direction, which is an important consideration for bending, but we will skip that for this tutorial and go ahead and click OK. Next, we go to the Process Material Library to set the size of our stock sheet metal. I work in metric units, but all my stock material comes in US customary units. So my 4 by 8 foot sheets are 1219 by 2438 millimeters. I need to set the package length and width to these values for both the 6.35 and 1.5 millimeter thicknesses. If we click on the parent material and then go to the nesting tab, here is where we set the minimum separation of components on the same sheet. The biggest driver for this value will be the lead in and out distances, so you have to think ahead on how you're going to program your toolpaths. For any parts under 6 millimeters or 1/4 inch thick, I use a separation value of 8 millimeters. For thicker material, this will be increased as larger lead-ins are needed. Once that item separation is set for both sheet metal thicknesses, we can click OK to exit that dialog. Finally, we will click on the Create Nest Study button. In the first tab, we can set how many copies are needed. If I wanted 2 complete mill enclosures, then this value would be 2. The stack size is if you're cutting multiple sheets at once. This doesn't work well for plasma cutting, but it is useful for other cutting techniques such as water jet. The Shape tab lists all the parts that will be cut. The Packaging tab shows the sheet metal sizes that we set in the Process Material Library. The Global Parameters tab sets the nest computational settings. The corner position determines where to start the nest. As I typically set the origin of the cut to the bottom left corner, I want my nest to start there too. The minimum and maximum compute time determines how long Fusion attempts to organize the parts. The more parts you have, the more combinations of positions and orientations that they can be arranged in. More complicated models or slower computers will require longer compute times to converge on the most efficiently packed results. The desired yield is how much of the sheet metal must be used as a percentage before Fusion can return a successful layout. The max part density will be strongly dependent on the size and shape of the parts that will be cut out. 80% is fine, but it's worth playing around with this value to maximize sheet usage. Remnant refers to the leftover sheet metal after a cut. Through the remnant optimization setting, you can select whether you would like the excess sheet metal to be preferentially along the length or the width of the material. In the Output tab, we want to make sure the Create Manufacturing Model is checked. Clicking OK will start the nesting process. In the browser, you can track its progress. Of course, how long it will take will depend on the computing time you set and the desired pack density. Once finished, we have 2 nests, one for each thickness of material. Just clicking through the results, you can see how efficiently it packed all the parts. In this sheet, it was able to stick several parts in the cutout present in the front of the enclosure's base. Each nest is composed of 4 sheets, so it will take at least 8 sheets to make this enclosure. There is some leftover material or remnant on both of the 4th sheets. From here, you go through the same steps as I showed in the first part of the CAD section for generating toolpaths. The only difference is that you would create a setup and 2D cut profile for each sheet. But there you have it. While you do have to pay for this feature in Fusion, as you work on more complicated projects or cut out many parts, automatic nesting is an invaluable tool. This concludes the CAM section, but if you made it this far, then definitely stick around for the plasma cutting montages at the end of this video, including the vacuum lifter and fire pit. But this is where I'm going to leave you, so with that, I'll catch you in the next one.
I can't stop.